and the opportunity to talk about the technology of glass bulbs used in fire sprinklers. I want to start the presentation with the question, these two types of glass, obviously they are not the same. As Paris and Russ have mentioned yesterday, sprinklers have to pass a series of tests, like corrosion tests, puncture tests, blast tests. And the glass on the left side can probably be used in California, but should not be used for fire sprinklers. During the presentation, I want to cover a little bit of the design of glass bulbs, how they function, how they operate, and how they are manufactured and inspected. Finally, we will outlook what kind of technology is coming next. We started the design of a glass bulb with a 3D model using 180,000 elements. This model assumes that it's a static load case and that the material under load stays linear and elastic. The principle of the axial stress, the negative values are compression stress. It's important to have a compression stress because glass only breaks if there's a tensile stress present. We've done this modeling on the outside of the glass bulb and also on the inside. In addition to model glass bulbs without any load, we have modeled them with an internal pressure about 250 bar. That is the bar, the pressure, the internal pressure when the glass bulb breaks in the fire zone. And you can see on the lower picture, the stress level is highest in the cylindrical part. And this is the area where the glass bulb starts to break. There are two different levels of breakages. It's the low level and the high level breakage. Glass starts to break one origin. And from this origin, the crack propagates into two directions. And if the crack reaches a certain speed, it divides into several smaller cracks. And that is what you can see on the right side. This is what we want to have in the glass bulb and sprinkler. If we have low, or would have a low level breakage, the sprinkler operation would look like this, so that the glass bulb breaks, but will not give the waterway free for extinguishing fire. What we want to have thousands of small glass fragments when the sprinkler operates. For that reason, we have to introduce a certain stress level into the glass bulb. You can see a typical stress level on the upper picture. On both pictures at the bottom, there are stress levels of glass bulbs assembled in the sprinklers. On the left side, at the point of contact, so nearly zero load, and on the right side, the assembly load of about 800 mm. So that's a very high load of the bulb, and you can see the difference in the stress. This is the way that the sprinkler should operate. The glass bulb breaks on the second picture from the left side, gives the waterway free, the pip cap and the seal gets out of the sprinkler, and the water is extinguished. In reality, it looks like this. Unfortunately, the sprinkler is upside down, so it's a pendant sprinkler shown upright, but I have not been able to change the drawing and turn the drawing. But you see how the glass bulb breaks, very lot of small fragments, and allows the water to get out. And manufacturing glass bulbs, everything starts with the glass that is used to make these, and everything is about a zero failure strategy. Because in some applications, like residential sprinklers, there's sometimes only one sprinkler in the room, and if one sprinkler fails, the sprinkler system fails. For that reason, we do a 100% incoming inspection, although we use the best glass of the best supplier that is available in the market. We sort out quite a portion of the glass. So we look for impurities, scratches, air bubbles inside the glass in order to make sure that only the best glass is used for the continuous working steps, and all failures that are bigger than 5 micrometers are sorted out. Afterwards, the glass is classified in different weight classes in order to guarantee a very uniform production. And this is an example of the weight classes that we have using the glass from the short supply. The problem is that we've recently seen some quality issues, as you can see on the right side. For that reason, we have decided some time ago, in order to avoid this, to make our own glass. We do not melt the glass, but we draw the glass to the right dimension that we want to have. This is the process. So this kind of machine was developed and actually was funded by the German government. Since this technology is not on the market available, or wasn't on the market available, we've implemented this, and you can see the glass is drawn very uniform. The machine is loaded with tubes of big diameters, up to 20 millimeter diameter, and the glass is drawn to the dimension that we want to have. You can see it's very precise and well controlled. And having the same test with this glass coming from this machine and measuring the weight classes, you can see the difference. Coming from 10 weight classes that we last purchased, we have now only 2 weight classes. So at the end of the day, this is a quality improvement of about 60% compared to the glass from shop that we purchased. After that, we have the glass tubes, but we want to make these glass bulbs out of these, and this is done in the area of the machine room. So there are several machines dedicated for specific diameters. The machines are designed especially, in-house designed especially for this kind of application. So about a 30 station machine. And the glass bulb that comes out of this machine is 100% measured. So we measure about 50 dimensions, and we do this 12 times while the glass bulb is rotating in order to measure any eccentricities that might occur. So about total 600 measurements are taken on each single glass bulb, and if one of these dimensions is out of the specification, the glass bulb is automatically rejected. With this data we obtain, we use them for statistical analysis, we use them for process control, and all data are saved in the system, so we can trace it back very good. This is the type of glass bulb that comes out of this machine, but the glass bulb that you know out of the sprinkler has something inside, is sealed and marked. And the following processes are on the filling and welding and testing line. So this is a machine designed from us, especially for these applications. And in this machine, there are only 2 steps that add value to the product. That is the filling and the sealing. All the other steps that you can see on this machine are for quality control, for quality checks. For example, after filling, we need to check whether the glass bulb is filled in order to make sure that we are able to calibrate the glass bulbs at the end. We do the welding, it's automatically filled, it's automatically welded, and again, there's 100% control over welding. There are several dimensions that are checked automatically, and again, a lot of statistics are done with this measurements to do production control and again for the traceability. Glass bulbs or sprinklers only operate when the glass bulb is able to build up an internal pressure. As mentioned before, the pressure inside the glass bulb is about 250 to 300 bar when it operates, and we have to check this. For that reason, the glass bulb is heated up close to the lower limit of the operating temperature, and this shining red area in the center of the glass bulb indicates that this glass bulb has built up an internal pressure. And this is good and acceptable for the next step. If there would be a tip breakage or some damage to the wall, it would stay black inside and would be rejected automatically. There's an additional tip control. We've done this directly after welding, but since the tip of the glass bulb is one of the sensitive parts, we have another control with 50 pixels while it's rotating. And during the welding, like it's welding of every material, you have different, or you have high temperature differences. There are some stress areas. For that reason, double check or control the stress area, especially the tip area, whether the position or the amount of stress is acceptable or within the tolerances. And on the right picture, you can see there's a bubble inside the glass bulb. So in each glass bulb, there's a bubble with a certain size that determines the operating temperature. And we measure the volume of the glass bulb. It's easily to sort out glass bulbs that would operate too early in the field, simply by heating them up to the lower limit. But it's very difficult to sort out glass bulbs that would operate too late. So these glass bulbs have a bigger bubble than specified, and these glass bulbs are sorted out at that step. At the end of this production, the glass bulbs are marked with the type, and each single glass bulb is marked with batch number. That guarantees or gives the possibility to trace it back. So all production-related data are saved to this batch number, and also the material data, raw material data from the supplier, the glass, the liquid, and everything that is used to manufacture these glass bulbs are related to this batch number and can be traced back. And in order to make sure that the marking is readable and is on the glass bulb, we have a control. In parallel, we do sample tests taken from each batch. Since the approval agencies require strength tests, operating temperature tests, sensitivity tests, we do this batch-wise during the production process. So on the left side, there's, for example, the strength test, where the glass bulb is loaded between two loading points, and the strength is increased by 250 Newton per second, according to the standards, and the glass bulb breaks and it's recorded. The same with the bars test and with the sensitivity test. At the end, we have a quality control record with each batch that shows that all tests have been done, and it shows some test results, some important test results, that's the bulb strengths, together with the information on minimum strengths, maximum strengths, TL values, and on the bottom we have the operating temperature test results with minimum maximum. On each record, it's production rate type. So in total, each glass bulb that is shipped out has undertaken more than 900 measurements in order to guarantee quality for life safety product. Because can you imagine if you install a glass bulb that looks like this? I mean, this will definitely not operate. It will probably build up a small internal pressure, but then the tip will fall apart. Same with these dimensions, and if the crack is only on the surface and it's not gone through, it's difficult to identify and it's installed because the liquid is still inside, but it will not operate. So what is coming next? There's a new design that's not cylindrical on the outside anymore, that has a shape on the outside. We've done some analysis models with these and have seen that the resistance against side impacts is more than doubled in this glass box. But this is only one thing